Relativity! Part 2, General Relativity. Before we jump into the wonders of general relativity, we should first cover one last bit of special relativity. When one views a moving object, that object will become shorter in the direction of its movement. Like most aspects of special relativity, this isn't noticeable at normal speeds. At 60 miles an hour, an object may seem to be a little shorter simply because it's going fast, but that's just an optical illusion. At very high speeds, close to the speed of light, what are called relativistic speeds, it is not an optical illusion. Objects will literally, physically, decrease in length in the direction of their movement. So that's three bizarre things that happen to an object going very fast. Its mass increases, it slows down in time, and it becomes shorter. This shortening is called a Lorentz contraction. But enough of that weirdness. Time for general relativity. If you remember from part 1, there is a difference between inertial and non-inertial reference frames. Galileo postulated, and Einstein confirmed, that all inertial reference frames will feel the same no matter how fast you're going. Einstein took this a step further and said that all non-inertial reference frames will also feel the same. They'll feel different from inertial reference frames, but they will feel the same. For example, even just standing on the Earth, you're not in an inertial reference frame. True, nothing around you is moving, but there is a constant downward pull due to gravity. In a truly inertial reference frame, you would be in free fall. There would be no forces acting on you. So in part 1, I was really just lying to you the entire time. Sort of. You can only be said to be in an inertial reference frame on Earth if you're only dealing with side-to-side movement, like if you're on a train on a flat track. Otherwise, the pull of the Earth's gravity prevents it from being a truly inertial reference frame. Now, one method conceived to help space travelers adjust to the lack of gravity out in space is to have a hollow donut be part of the spaceship and have this donut rotate. This method was showcased in the movie 2001: A Space Odyssey. Remembering that a velocity is a speed in a given direction, that velocity can be changed not only when the speed changes, but when the direction changes. Changing the speed or direction of a velocity is called acceleration. So if you're sitting in the spinning hollow donut, you are constantly accelerating because your velocity is constantly changing direction. Now, due to the law of inertia discovered by Newton, things in motion don't like to change speed or direction. So your body wants to go in a straight line, but the spinning donut is pushing you in a different direction. The donut pushes you inward, but because your body wants to go in a straight line, it feels like you're being pulled outward, which sticks you to the wall of the donut, and it feels just like gravity. Because of general relativity, this would feel exactly the same as being in an accelerating rocket. A change in speed or a change in direction will both create a force against your body, and all forces feel the same, whether it's a physical force like a push or pull or acceleration, or a force like gravity. So according to Einstein, standing motionless on the Earth, being pulled downward, feels exactly the same as being in an accelerating rocket or a spinning donut in space. Now, Einstein's explanation for how gravity works is a bit weird. According to general relativity, any mass will warp the fabric of space-time. The classic demonstration of this is the image of balls on a rubber sheet. The heavier the ball, the more of a depression it will make in the sheet, where the sheet is supposed to be space-time and the ball is supposed to be a mass. But this is misleading, because space-time is four-dimensional, where the sheet only has 2 dimensions. And there's also no such thing as up and down in space. Everything is relative. Instead, imagine that space-time is a great big sheet of graph paper, all nice straight lines, and a mass will pull those lines in, distorting them. So anything coming in along one of those lines will have its path changed as it nears the mass. If this anything comes close enough to the mass, or the mass is large enough, the path will keep changing and the thing will curve around the mass until it just starts going around the mass. This is how an orbit is formed. An object in orbit around a mass is essentially just falling very slowly at a very shallow angle. Now, orbits, contrary to popular belief, are never circular. They are always elliptical. An ellipse is essentially a circle, but unlike a circle which has but a single center, an ellipse has two focal points. In an orbit, the larger mass in the solar system, this would generally be the Sun, occupies one of the foci, while the other focus is empty. Now, since an orbit is an ellipse, there is a point where the orbiting body comes closest to the central mass. This is called periapsis. Now, since nothing in nature is perfect, that periapsis will slowly change position. This is called orbital precession. Now, orbital precession can also be explained by classical mechanics, but around the time that Einstein was figuring out general relativity, it was found that Mercury's orbit was precessing a little too fast, at least according to classical mechanics. General relativity was able to accurately predict Mercury's orbital precession, which is faster because Mercury is so close to the Sun in space-time that's a bit more warped. Now, normally, a mass simply bends the space-time around it, and this bending allows scientists to accurately predict how fast an object would need to travel to leave a massive body's surface. This is called the escape velocity. A greater mass will mean a greater escape velocity. On the Earth's surface, the escape velocity is 11,200 meters per second. On the Sun's surface, it's 617,500 meters per second. Of course, the size of the object also matters because a larger object's surface will be further away from its center of mass. If you remember, the speed of light, the speed which nothing in the universe is able to go over, the universal speed limit, is 300 million meters per second. Scientists long thought about the idea of an object so massive, yet also so small, that the escape velocity at its surface would be greater than the speed of light, which would mean that no light, and indeed nothing else, would ever be able to leave its surface. This is called a black hole.
One further peculiarity arising from general relativity is that, analogous to how traveling at high speeds will slow you down in time, being in a gravity well will also slow you down in time. So if we imagine there are two twins, Terra and Luna, and they're born within seconds of each other, but Terra was born on Earth, and Luna was born on the Moon, then Luna would age more quickly, because Luna is going through time more quickly because the Moon, having a lower mass, creates a smaller gravity well and therefore warps space-time less. This has actually been proven. Atomic clocks have been taken into high orbit around the Earth, which takes it out of the gravitational well of Earth, and when these clocks were brought back down to Earth, there was a discrepancy between them and the clocks that remained on Earth. An oft-evoked image is that if a clock were dropped onto the surface of a black hole, it would stop. Just like a clock carried on a ship traveling at the speed of light would stop. This is probably the biggest point made by the theory of relativity, that space and time are part of the same thing, and whatever affects one will affect the other. So going at high speeds will slow you down in time and shrink you, and mass will warp space and time, giving rise to the effect we call gravity.
So now you know everything there is to know about relativity, though I would definitely recommend getting out a book or taking a class on the subject, as this is really just a summary.